is the top of the ladder moving? When the base of the ladder is 8 feet from the wall, how fast is the top of the ladder moving? So as a derivative, what are they asking us here? dy dt. Find dy dt. How fast is that distance y changing as time goes by? Okay. And what's given to us? The rate at which it's pulled away from the wall, that's dx over dt. And is that positive or negative 1? Positive, because x is getting larger as this ladder moves that way. It's moving at a rate of 1 foot per second. And they want to know what dy over dt is at the moment when the ladder is 8 feet from the wall. So what is that, x or y? X. So they want to know this when x is equal to 8. Okay. What equation did you use? Once again, at any given moment, you have a right triangle. Believe me, we'll get to examples that doesn't use Pythagorean theorem, but this one still uses it because you have a right triangle, right? Yeah, a lot of, maybe 50% of the questions may be using it in this section, yes. So we have, once again, y squared. An equation that relates all the variables is y squared plus x squared equals to 20 squared, or 400. Now I'm going to differentiate both sides with respect to which variable? Always t, right? Things are changing as time goes by. So it's going to be 2y times dy dt, right? Plus 2x times dx dt equals to what? What is the derivative of a constant of 400? 0. The rate of change of the ladder is 0. It doesn't change at all, so this should be 0. Okay. Now, we can divide both sides of this equation by 2, so we can get rid of these unnecessary constants here, making our equation a little bit easier. Now, I need to have y times dy dt. Well, they give us x, so at the moment, I don't know what y is, but can I figure it out? Yes, if x is 8, y is unknown, and this side is a fixed number of 20, we can get what y is, once again, using the same equation over again. Y squared plus 8 squared equals 20 squared. So y squared equals 400 minus 64. So y will be, I believe, the square root of 336. You can either get a number for it, or you can keep it like that, only round in the last step of your approximation. You can also do it that way. Either way is okay. So now that we know what y is, we can plug it in. Y is root 336. How about dy dt? Do we know what that is? That's what we're trying to find, so it's okay to keep it as such. Just keep it as dy dt in your equation. Plus, x is given as 8, and dx dt was 1. So the only unknown now is dy dt, and we can solve for it, right? I will subtract 8 from both sides and divide by root 336. Anybody who got a decimal answer for us? And it should be negative, right? Negative 0.4 or 0.44, either one would be okay as far as I'm concerned. So, and the units would be feet per seconds. Does it make sense that this turned out to be a negative quantity, dy dt? Because if that ladder is being pulled away on the bottom, the top is getting shrinking, right? The top distance is getting closer and closer to the ground, so dy dt is negative, and that makes sense in this situation. Now, I'm going to add a part B to this problem, part B. So would you please just add this following question. So we have the same picture, but this time I'm putting an angle of theta. The theta is the angle between the ladder and the horizontal. The question asks, find the rate of change of the angle theta at the same moment, at the moment when x is 8. Find the rate of change of the angle. Finally, we'll step away from the Pythagorean theorem here. So once again, we need the goal, we need to state what's given, and then we need to find an equation that relates all those variables. Let's begin with the goal. As a derivative, what are they asking here? Good. d theta dt, the rate of change of the angle theta as time goes by, that's precisely d theta dt. That's what they want to know. Find d theta dt when x is equal to 8. At the moment when x is 5, the base of the ladder is 8 feet from the wall. Okay. The given information is the same as given in the top of the problem. And that was the base of the ladder was moving at a rate of, so that part of the problem hasn't changed. And what was that rate? Positive 1 foot per second, because this ladder was being pulled away in that direction, right, at a rate of 1 foot per second. That hasn't changed. Okay. But the equation has changed, because somehow you need to relate theta and x. You need to have theta and x in the same equation. What kind of an equation would that require? Definitely not the Pythagorean. There's not going to be an angle theta in there, right? So what equation could we use? We need a trig function here. To get a theta in there, we're going to need a trig function. Then the question becomes, which trig function would be the best one to use? We want to relate the side x. And you definitely want to make use of the hypotenuse of this triangle, which is it's a fixed length. You want to use that in your equation. So cosine would be a really good choice here, because cosine would relate the adjacent side with the hypotenuse. That will work very well. Now, since we also did part A of this question, we also know what dy over dt is, right? In that regard, you could also use sine function, because you can then revert to your dy dt. But let's just keep it simple. Let's just use the cosine function as you suggested. So here's our equation we're going to use. Cosine theta equals, what is it equal to? In terms of variables first, x over 20. Right, adjacent over hypotenuse, that's x over 20. Okay, now we want to differentiate with respect to the variable t. And what do we get? Differentiate with respect to t. Okay, derivative of cosine theta with respect to t. Let's think about it. Remember, theta changes with time, right? Theta is a function of time. So what is the derivative of cosine of theta with respect to t? Good start. Negative sine theta times d theta dt. Okay. The right-hand side, I can really write it like this. 1 over 20 times x. I don't need the quotient rule there. It's a constant times a function. The constant remains. I just need to know what is the derivative of x with respect to time. Derivative of x with respect to t. That would be just 1 times dx dt, right? Or just dx dt. Okay, any questions about my derivative here? Any questions? Yes. At the end. At the end, when we're determining like sine theta, we're going to use that right now. Again, it's very important to remember. First you differentiate, then you substitute your constants in. Okay, if you plug them in too early, you're going to lose your equation. You won't have anything to differentiate, basically. Okay, so now we need to find dx over dt, of course, is given. That's no problem. So this is 1 over 20. Dx over dt was 1. I might as well put it in there. D theta dt, again, that's a good variable to have in your equation, because we're looking for that, right? We're trying to find d theta dt. The only thing that we need to know right now is sine of theta. And let me not forget the negative. I'll put it here. I need to know what sine of theta is in this triangle. Let me draw it down here. I need to know sine of theta. So this side is 8. This side is 20. And didn't we already know what y was also from the previous work that we did? What was this? Root 336, right? So we already got that in the last step, root 336. So I need to know right now sine of this angle theta. So what should I have? Exactly, opposite over hypotenuse, which is root 336 divided by 20. Opposite over hypotenuse for the sine. And finally, to solve for d theta dt, when you're dividing by this fraction, both sides, it's basically going to appear on the other side as the reciprocal fraction, right? So it's going to appear as negative 20 over root 336 times, we already have 1 over 20 there, and the 20s cancel exactly. So let's see now, what is negative 1 over root 336? That is going to be the rate of change of that angle per unit of time. Time was in seconds here. And anytime you're using calculus to get an angle, you have made certain assumptions, like the area of sine is cosine only when theta is in radians. Okay, if it's not in radians, there's an extra factor there of like pi or 180 or something like that. So anytime you use calculus to get to a point, your answer will always automatically appear in radians per second. In this case, theta will automatically be in radians when you get it back here. So is it decimal? Did you get 0.0 something? 0.055. And the units would be units for theta over units for time. That's going to be radians per second.